Hello, this is Mrs. Hanson, and I am going to walk you through some of the Chapter 12 Kinetics, no calc practice. Okay, so as I've told you guys before, nobody in their right mind should watch this whole video from beginning to end, but rather just sort of scroll through to the questions that you have questions about and see if I can maybe clarify some things or answer some of your questions, okay? And for heaven's sakes, if I don't answer your question in this video, be sure to talk to your teacher because the only dumb question is the question you don't get answered. Okay, so let's start with question 1. Okay, so this one got this long story about basically magnesium reacting with HCl, and it basically says, okay, which set of conditions would produce the highest rate of production? So the fastest reaction rate, okay? And hopefully as you're looking through, you're thinking to yourself, well, definitely a 3 molar solution of HCl that's a higher concentration, that's more collisions in a certain space, is going to produce more effective collisions than 1 molar. So that would put A and B out of the running. So, but looking at letter C and D, now you also have the magnesium pieces. So you think to yourself, oh, 1 centimeter piece versus 0.5 centimeter piece. But be very careful because in the language here, this line right here is really important. It says the volume of hydrochloric acid and the total mass of magnesium were held constant. So if you have 1 centimeter pieces and 0.5 centimeter pieces, they're still going to add up to the same mass. So you would need more of the 0.5 centimeter pieces to add up to some common mass. Okay, so that being said, what they're really saying is that we're talking about 1 piece of magnesium or like 2 pieces of magnesium. Which one has greater surface area? Okay, and basically smaller pieces always win. Because smaller pieces are going to have more exposed reactant particles available to do collisions. So the best answer is definitely letter D. Okay, a greater concentration of HCl, more collisions, and smaller pieces for the solid material means more surface area, more exposed reactant particles. Okay, so that would be number 1. All right, let's take a look at number 2. So we're looking at this data, and it looks like it's a classic differential rate laws, meaning you basically have a couple different trials and you're messing with the molarity, seeing how the rate's affected. So number 2 says, okay, calculate the rate law. Okay, well, let's decide what trials to look at. So I think it definitely looks like looking at trials 1 and 2 would be a good idea. So we're going to keep A constant, but we're going to double the concentration of B. And what I notice is that the concentration quadruples, 1.8 going to 7.2. So that's a times 4 increase. So it looks like it's second order in terms of the concentration of B. Okay, just to write that a little, so not very legible, is it? So I'll write that one more time. So we held this constant, we doubled this concentration. Whoops, that doesn't look much like a 2, does it? We doubled this concentration and the rate quadrupled. Okay, so that would be second order. Okay, so let's see, which ones do we want to compare to figure out the concentration of A? It looks like 1 and 3. So if you look at trials 1 and 3, B is held constant. So we're doubling the concentration of A, and it looks like the rate is doubling. So I would say this is a pretty straightforward rate law question, and it looks like the rate law would look something like that. Okay, so first order in terms of A, second order in terms of B. So it looks like the best answer there would be, indeed, letter D. Pretty straightforward? Okay, good. And just keep in mind that this kind of work, if you call it that, is great for like a multiple choice question, as long as it's a pretty straightforward example. But if it was a short answer, definitely you would have to provide a little more validation to support your answer than what you see here. Okay. All right. So let's see. Let's go on to number 3. Okay, so this one's kind of a fun one because it looks like a simple differential rate laws again, but you just have to do some counting because you have these molecular drawings to look at instead of just numbers. So let's see what we got here. First question says, if the reaction is determined to be first order in terms of A, okay, what will be the rate for trial 2? Okay, well, let's see. So what's going on from trial 1 to trial 2? So X is the triangles. Let's see, we got 1, 2, 3, 4, 5, 6 of them. And over here, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we basically doubled the concentration of the triangles, the X, okay? So we could say concentration of X doubles. So it being first order, that means the rate would also double. Classic first order kinetics. So I would say the best answer would be definitely letter C. Okay, the rate's going to go from 0.1 to 0.2 because doubling the concentration of X will double the rate. All right, so just figured that out by counting the number of particles in the box. All right, so that's pretty straightforward. Now, what's the order with respect to Y? Okay, so let's see how Y, what trials do we want to look at to compare Y? So what would be really nice is if X was held constant and that we just change Y. So, well, let's see, Y is the squares. So I see here, it looks like we have 6 squares here, and then 3 here. Okay, so it looks like we're cutting the squares in half. But I think I'm going to compare trials 1 to trial 3 because in trial 1, we're keeping the triangles constant. Okay, so that means by keeping the concentration of X constant, the only thing that we changed is we basically took the Y concentration and cut it in half. Okay, times 1/2, cut it in half. And let's see what happens to the rate. And it looks like the rate stayed exactly the same. So what that tells me is that it must be zero order in terms of Y, because even though we cut, the only change between trial 1 and 3 is that we cut the concentration of Y in half, and the rate stayed exactly the same. Okay. We kept the triangles constant, so that was kind of a non-issue. So it looks like this reaction is zero order in terms of Y. What do you think? Pretty straightforward? Okay, so we're moving right along. Let's see, we're looking at question 5. It says, what is the value for of K for a first order reaction with a half-life of 23 seconds? So one of the formulas you definitely want to know is that for first order reactions only, the half-life can be simplified as natural log 2 over K, or better yet, 0.693 divided by K. So natural log 2 is 0.693. Okay, so I think that's the formula we're going to want to use. So we got the half-life and we're looking for K. So I think we're just doing some simple algebra here. So let's see, 23.1, okay, and that's seconds, equals 0.693 divided by K. All right, so we're going to get K all by its lonesome. So I'm going to go ahead and multiply both sides by K. Let's see, times K, and then to get rid of the 23.1, I'm going to divide both sides by 23.1. Okay, so effectively it's 0.693 divided by 23.1. Okay, so hopefully, I think you can probably tell that the answer can't be 16 because 0.6 divided by 23 is obviously going to be a decimal. So we would say that A and B are out. So that leaves us to C and D, and they're the exact same number. The only difference is the units. So looking at the units, the top is, of course, unitless because natural log of anything doesn't have units. And then 23.1 is seconds. So it looks like the units would be 1 over seconds, which supports letter C. So another way you could write that is seconds to the minus 1. Okay, so not too bad. So we did that without a calculator, but gosh, by golly, we really didn't have to calculate anything. Okay, it was more like knowing what formula to use. Okay, so that's a pretty good one. All right, so let's take a look at number 6. I'm going to go ahead and make some room here. Number 6, so it says, in a chemical reaction that has first order kinetics, what is true at a constant temperature? Okay, well, here's a little simple grid that might be helpful to you. So you got first order, second order, zero order. So in terms of K, at a certain temperature, they're all going to be the same. Like K does not change. The only thing that changes K is temperature and adding a catalyst. And then for T1/2, okay, for first order, it's going to be constant. So if the half-life is 5 minutes, it's going to be 5 minutes. It's going to be 5 minutes. It's never going to change. For second order, the half-life continually doubles. So if it was 5 minutes for the first half-life, it'd be 10 for the second half-life, 20 for the next half-life, 40 for the next half-life. And for 0, the half-life cuts in half. Okay, so that's kind of helpful. So if the half-life was 5 minutes for the first half-life, then it'd be 2.5 minutes and then 1.25. Okay, so this is, good stuff to know. All right, so for first order kinetics, it looks like we're looking down this column. So it looks like half-life and K would both be constant. Okay, B, I would say corresponds to none of the orders. C, half-life is constant, but K changes. Does not correspond to any of the orders. And half-life changes, but K is constant. So that would be, I guess, second or zero order would both fit that description. Okay. Alrighty, so that's number 6. Let's see. And by the way, if there's anything that you want to study, let's see. I'm going to switch. Whoops. I'm going to show the desktop here. Hopefully this is the right document. Nope. There we go. I would definitely suggest that you really spend some time with this nice kinetic summary, and don't memorize it. But for heaven's sakes, like, you should be able to basically look down a column and make sure why all these things make sense for zero order. Okay, why all these make sense for first order. So if you need some help with that, don't hesitate to ask your teacher. All right, number 7. Ooh, a mechanism question. I love it. So it says the reaction, blah, 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 is found to be first order. So I'm going to go ahead and write the rate law. Let's see. So rate equals K, and it says first order in terms of R2 and zero order in terms of Q. Okay, so that's basically what they're describing the rate law as. Now, just keep in mind that when something is raised to the 0 power, that's basically 1. So this kind of really, you can drop it out. It's not really part of the rate law. Okay, so no matter what you do to the concentration at Q, it's not going to change the rate. Okay, so now it's kind of a matching game. So one of the rules with mechanisms is the rate law of the slow step has to match the experimentally determined rate law. So I'm just going to go through each of these mechanisms and just write a rate law. So for this one, let's see, K, Q first, R2 first. Okay, well, that is not a match because it has Q and R2 involved in the rate law of the slow step. Okay, so those don't match. Now B, okay, that one does have Q, has Q in the rate law, and that's not going to work, and it would be second order in terms of Q, so that is not a match. So I look at C, okay, this one, let's see, it's got Q, first order, and Z. Well, that is totally not a match, okay? So finally I look to D. If you look at the slow step, it is indeed R2 raised to the first order. So this is a match. So this matches the experimentally determined rate law. So the bottom line with Q is that it's not part of the rate law because it's zero order. So Q cannot be part of the slow step. So it's fine that Q is part of one of these other steps. Okay, so it looks like D's the answer, but I might suggest one other thing to check is that for a mechanism to be a good one, all of the steps should add up to the overall. So kind of like Hess's law, let's see, if I see something on the reactant side and also on the product side, I can simplify it out. So we got 2 R's here and an R here, so they cancel out. RQ also cancels out. Those are both intermediates. So R and RQ are both intermediates. The only thing left is R2 plus Q yields R2O. And that does indeed match the overall reaction. So those are 2 big points that make this mechanism good. The elementary steps add up to equal the overall, and the rate law of the slow step matches the experimentally determined rate law. Great question. I absolutely love that one. So that's number 7 about mechanisms. All right, let's see what else we got. Ooh, a graph. So for number 8, it says which is true of the reaction diagram for the elementary reaction such as the one shown. So the key with elementary is that just means that we're looking at elementary steps. We're looking at steps of a mechanism. So for this one, this is like a one-step mechanism because there's only one hill, okay? So what that means is it basically, let's see, has one transition state because that would be at the top of the hill. You might call it an activated complex, and it doesn't have intermediates. So the answer is B. But I think what might be helpful is what if I show you one that kind of fits some of these other choices. So let's say it was an exothermic reaction, but it had 2 elementary steps, something like that. Then you would say, oh, it has 2 transition states, okay, or activated complexes, and it would have 1 intermediate. Okay, so that 1 intermediate is just that little place in between the 2 humps, okay? So what do you think? Does that make sense? Okay, good. So that was a fun one. Let's see what else we got. So number 9 says, which is a correct explanation for why the rate of a chemical reaction increases with increasing temp. Okay, so just keep in mind, let's see, when you think about an energy diagram, when you increase the temp, you simply are you're going to have all these collisions, but if you increase the temp, you're going to have more forceful okay, and just greater number of collisions. So you're going to increase the number of effective collisions during a region of time. So that being said, let's see, the reaction becomes more exothermic. Not true, because that has to do with basically delta H, and nothing's changing there. It's the same products, it's the same reactants, so nothing's going to change about that level just because you increase the temp. So not a factor. The enthalpy of the reaction increases. Well, that's really saying the same thing as A, has to do with delta H. Okay, and that is just not changing. The activation of the reaction decreases. So that would be like this, like you actually lower the activation energy. Not happening here, because that's what would happen if you added a catalyst, okay? But here, we're not doing that. So the activation energy is still exactly the same. But more of the colliding particles have the activation energy. So the whole crux of the matter is, if you increase the temp, you're just going to increase the percent or fraction of effective collisions that can overcome that activation energy. Okay, so D is definitely the best answer. Okay, what else do we have? Let's see, number 10. This one, I have to admit, is not the best phrased question. It says, how would the net ionic equation written for a catalyzed reaction differ from the net ionic equation written for the same reaction without a catalyst? Like honestly, if like A was reacting and turning into B and you had a catalyst, you would simply write it over the arrow. That's how we notate the catalyst. So which of these choices really say that? Let's see, the net ionic would be different because an additional reactant is needed. No, because the catalyst is not really a reactant. B, the net ionic equation would be different because the catalyst should be shown on both the reactant and the product side. I mean, technically you could show that, like that is true. Like you start with the catalyst, you use it to speed up the reaction, and then it reappears. So like it kind of crosses out, but we just wouldn't show that. We just put it over the arrow. See, the net ionic equation would be the same because the catalyst is a spectator. Well, I mean, it does kind of cross out like a spectator, but a spectator truly does nothing. It does not contribute to the reaction at all, and a catalyst is clearly doing something. Okay, it's speeding up the reaction. So C is not a good answer. So that leaves D. The net ionic equation would be the same because a catalyst is neither a reactant or a product. So I think that's the best answer. Catalyst is just something that speeds up the reaction. Write it over the arrow. Okay? All right, let's see what else we got here. So 11. The following reaction was determined to be elementary. So again, what that's telling you is that we're describing a step in a mechanism. So what that really means is that the coefficients should be the orders. So it says, what is the overall order of the reaction in the units? Okay, well, for elementary steps or steps in a mechanism, the coefficients are the orders. So this would be first order A and first order B. So therefore, if you solve for the units for K, it is second order overall. And if you guys remember anything about determining units, for K, it's basically 1 molarity less than the total order per unit time. So basically it's 1 over 1 molarity less. So if it's squared for the overall order, then we'd have 1 molarity left per unit time. Okay, and the time, it looks like they're not specifying it, so we can just use it as time. So that would be the units for K, 1 molarity less than the overall order per unit time. But they're writing it a little bit differently. So if molarity is on the bottom, that means moles is on the bottom. And molarity is moles per liter, so that means the liters would flip to the top. So that's like the inverse of molarity, or when molarity is on the bottom per unit time. So it looks like the best match is letter C. All right, so I think the key word there is just know that elementary is referring to a step in a mechanism, and it just means that you use the coefficients to determine the order, okay? Let's see, how about number 12? So this one, another graphing question. All right, it says the concentration of reactants versus time was measured and plotted for the reaction here, which is second order. Okay, so what that means is you got to really be careful with the units. So we're plotting concentration versus time. Okay, so which one of those fits second order? Okay, so again, going back to that summary sheet, this guy right here, it looks like the best match. So basically concentration versus time, concentration versus time, concentration versus time. We're looking at this last row, and it looks like the best match is indeed letter A. So it would be a curve. Looks a lot like first order, but it would be a curve, like more extreme curve, okay? So it'd be more steep at the beginning and more flat at the end. But that definitely looks like the best option since it's the only curve there. If you were tempted to pick C, I see what you're thinking, but that would be 1 over concentration. Whoops. Concentration versus time. That would produce a straight line for second order. Okay. And the slope would be K. But it's not saying that that's what the axis is. Okay. It's saying concentration versus time. Let's see. So just consequently, I guess this one, choice B, would be for zero order. Again, that matches the graph best because in zero order, the rate never changes. So it's a nice straight line because the concentration of A will go down at a constant rate. Okay. And D, honestly, I mean, it doesn't, I guess it would fit rate versus concentration for zero order. But that's really a stretch. That definitely doesn't match the axes that they're talking about. Okay. So I guess my piece of advice is with these graphs, really pay attention to what they're actually plotting on the axes. Okay. So there you go. So A is definitely the best choice there. Let's see. Letter B. Number 13. Ooh, another mechanism question. It says, okay, so many organic reactions, such as the two-step conversion of 2-butene to 1-butene, is shown below. Okay, and it does say it's a mechanism. Okay, so it asks, what is the role of the acid, the H3O+. Okay, well, looking at this two-step mechanism, okay, it looks like the H3O plus cancels out, and it looks like the water also cancels out. Okay, but the way that the H3O plus cancels out, that's what a catalyst looks like. Okay, so a catalyst is something that's there, okay, at the beginning, and then it gets used to speed up the reaction, and then it reappears so it can be used again. Okay, so that's a catalyst. It's there, then it disappears. Now, as it turns out, this guy, the water, is actually an intermediate. So an intermediate is just the opposite. It's made, and then it immediately gets used up. Okay, so it's kind of all about the order of which you see these things. Okay, but H0 plus is definitely a catalyst. All right, let's see, number 14, another mechanism question. So it says, okay, here's a proposed mechanism. It says, what's the rate law? Okay, well, like we talked about earlier, the rate law of the slow step is going to match the rate law for this reaction. So if I go ahead and take W raised to the first and then X2 raised to the first, okay? But, be careful because that is not the correct answer, okay? The reason for that is W is not one of the reactants, okay? W is an intermediate, okay? And you can't have an intermediate in the rate law. So then you got to go up to step 1 and say, well, where the heck did W come from? And what you'll notice is that this one's a little different than the one that we did in class because this is 1W, but this is 2 W's. Those have to match perfectly, okay? So what I'm going to do is divide this by 2. And basically cut the coefficients in half. So if I divide this, if I write it out, sorry. Okay, I'm going to cut this one by 2 and this one by 2. So I'm basically just cutting the coefficients in half to say that W is equal to basically 1/2 W2. Okay, so if you kind of just follow that through, because we're substituting in, but you have to make those match exactly. Okay, so what that means is that the rate law is still dependent on the slow step. Okay, so it'd still be the x squared raised to the first. But for that W, we're going to go ahead and substitute where it came from, which is going to be W2, and it's got a 1/2 in front of it, so it's going to be raised to the 1/2 power. Okay, so that would actually be the rate law for this reaction, which looks like it is choice D. So that was a little tricky, but I think what you guys learned is like I said, when you are trying to deal with that intermediate, just have to make sure that what you're substituting in exactly matches. So if you have to manipulate one of the steps a little bit to do that, you absolutely can do that. Okay. All right. So that's a good one. Number 14. Let's see. So number 15 says, which energy profile represents the reaction that would occur at the lowest rate? So that means the slowest. So what we're looking for is the greatest activation energy. So without a shadow of a doubt, we can go ahead and plot that for each one of these. Okay, the height of the reactant level to the height of the hill. Okay, height of the reactant level, the height of the hill. Okay, and it looks like this guy's our clear winner just because this is the greatest activation energy. So it's going to be the slowest reaction. Ooh, I love that one. That's a pretty easy one. And finally, the last one, it looks like a basic question just about how to do kinetic stoichiometry. So it says, let's see, if you have this reaction, just basically how do the rates of formation and disappearance compare? Okay, so the correct answer is actually B. Carbon dioxide gas, which is right here, is being produced twice as fast as oxygen is being consumed. So read that really carefully. It's basically saying that basically the CO2 and the O2 are in a 2-to-1 ratio. Okay. The CO2, since it's got a 6 in front of it, is going to be made 2 times faster than the O2 is being used. Okay. You can go through and actually correct all the other ones. Like for letter A, methanol is being consumed at twice the rate of the water being formed. Okay. And I would say that's the exact opposite. Methanol is being consumed at 1/2 the rate at which water is being formed. Okay. Because the water is going to be formed faster than the methanol is being used. For C, the reactants are disappearing twice as fast as the products are appearing. Okay, well, that's interesting. So we're going to combine those together. So that's 5 moles of reactants disappearing to 10 moles of products appearing. So I would say the reactants are disappearing at 1/2 the rate of the products appearing. Would you guys agree? So it's kind of the opposite. And finally, D, the rate of production of carbon dioxide is twice the rate of disappearance of methanol. Well, they're in a 2-to-6 or a 1-to-3, so I would say maybe 3 times the rate of disappearance of methanol. So that one's a little bit tricky, but it's just reminding you of how kinetic stoich works, okay? And you can apply that in any reaction that you might look at. Okay, well, I think that was number 16. So it looks like I've gone through all of them. Again, please don't hesitate to ask your teacher if you still have questions, okay? I would rather get your questions answered before the test than ask for why you missed stuff after the test, okay? Well, thanks for listening and good luck with your preparation.